Welcome to this tutorial. I'm solving question number 6 of paper 2 October-November exam series of 2021, and the main topic of this question is half-life. Question says isotope X is radioactive and it decays by alpha particle emission. So the radioactivity or the radioactive emission from this isotope is alpha particles. To a stable isotope, state how a nucleus of X changes when it emits an alpha particle. So when a substance or radioactive substance emits alpha particles, we know that the number of protons decrease by 2 and the number of nucleons decrease by 4. An alpha particle contains 2 protons, 2 neutrons, so which decreases the proton number by 2 and the nucleon number by 4. Now the next part says there is a radiation detector in a laboratory where there are no radioactive samples. So since there are no radioactive samples, so no active source of radiation is present there. The detector is switched on and shows an average count rate of 22 counts per minute. Still, the detector is showing some radiation count rate. State why the radiation detector shows a count rate. It is because of background radiation. Due to sources like radon gas, cosmic rays, etc. So these substance and radioactive substances are normally present everywhere. A count rate is seen on the detector because of this background radiation. The next part says a sample of isotope X is placed 2 cm from the detector. So we are provided with the distance. It is 2 cm and the reading displayed is 8000 counts per minute. The sample is moved a distance of 10 cm from the detector. Now the sample is being moved away from the detector. The reading returns to an average value of 22 counts per minute. Explain why the reading returns to the original value. Alpha particles can travel less than 10 centimeters in air and are absorbed by the air between the source and the detector. So since the distance is too large, the alpha particles are absorbed by the air during this distance of traveling. The next part says an alpha particle passes into a region where there is a magnetic field. In the magnetic field, a force acts on the alpha particles so that it follows a circular path. Figure 6.1 shows that the particle passes through point J. On figure 6.1, draw an arrow through point J to show the direction of force on the alpha particle J. So the arrow would be drawn towards the center of this circular path. The force exerted on alpha particle is making them to move in a circular path, so there must be a centripetal force acting on the alpha particle, and centripetal force is always directed towards the center of the circular path in which an object is moving. Okay, the next part says determine the direction of the magnetic field and mark a tick in the box that indicates this direction. So the direction of the magnetic field could be found using Fleming left-hand rule here. We can see that the movement of the alpha particle is to the right. The force acting on the alpha particle is in the upward direction. So we would align the second finger with the current's direction, and thumb is going to give us the direction of the force here. So the first finger, it points out the direction of the magnetic field here, and it would be into the page. So this is how the Fleming left hand rule is used here to find the direction of the magnetic field by taking into consideration the direction of the alpha particles traveling, which is same as the direction of conventional currents traveling, the force acting on the particle because they are experiencing a deflection because of an upward force, and the direction of magnetic field using the Fleming left hand rule would come out to be into the page. So we are going to tick the box of into the page for this part. The next part says explain whether this force does work on the alpha particle as the particle move along the circular path. We know that the work done is the product of force and the distance moved in the direction of force. But we can see that here the particles are not moving in the direction of the force. So no work is done. I would explain it referring to the same diagram. We can see that the particle at every instant in a circular motion has the direction of the velocity along the tangent. So the direction of the velocity also tells us the direction of the movement at any particular instant of the particle which is performing the circular motion. The force always acts towards the center of the circle, but the particle moves in a direction which is perpendicular to the direction of the applied force. So no distance is being traveled in the direction of the force applied. That is why we would say that there is no work done here in this case. So the question ends with this part.
We try to explain complex concepts in simple language and with effective examples. If you like the video and the way we explain the subject, consider liking this tutorial, commenting on it and subscribing to our channel and press the bell icon, so that you stay updated and get notified when we upload more videos. Thanks for watching.